So for the next number of lessons, I'm going to be talking about kinetics. Now, chemical kinetics is the area of chemistry in which we're concerned with the speed of a reaction. So up until this point, we've been talking about how much of a product is produced, but what we're now going to talk about is how quickly a reaction occurs. And there are four main factors that affect the speed of a chemical reaction. The first one is the physical state of the reactants. Specifically, the more readily reactants collide with one another, the faster the reaction is. So keeping this in mind, molecules that are in the aqueous or the gaseous states are going to react much more quickly than molecules that are in the solid state. Now, if you do have molecules that are in the solid state, you want to maximize surface area, and you actually do this on a daily basis by chewing. By chewing, you're breaking apart molecules, which then can be exposed to a larger amount of all of the different enzymes that are going to break down your food. If you just swallowed your food, then it would take a lot more time for those reactions to occur. The second factor that affects reaction rate is the reactant concentration. Specifically, the more reactant you have, the greater its concentration, the greater the number of collisions are going to be, and therefore the faster the reaction is going to be. Remember, you want as many collisions as possible to increase the rate of reaction. The third factor that affects reaction rate is reaction temperature. Now, this is very similar to the point I just made, but as your temperature increases, your kinetic energy increases. So not only are you going to have more frequent collisions like in number 2, but you're also going to have collisions with greater energy, which means that the rate of reaction is going to increase. And finally, the presence of a catalyst is going to increase the rate of reaction, but catalysts themselves are not used up. So we'll look at catalysts in more detail later on in this big idea. Now, how exactly can we measure reaction rate? Well, there are two different ways to measure it. The first one is average rate. So the average rate, let's say, for example, I'm going to go from my house and I'm going to drive to school. Let's say I drive a total of 2 miles and it takes, 10 minutes for me to drive that distance, okay? So what I can do to determine the average rate of my driving is to take that 2 miles and divide it by 10 minutes, and that's my average rate. That doesn't mean that I'm going to be driving at that speed the entire time. It's an average of all the different speeds, of me speeding up, me slowing down, me having to stop. And so that's what the average rate is. And the way we measure average rate in chemistry is simply the change in concentration divided by the change in time, which is the same as what I said for the example with driving to school, the change in distance divided by the change in time. So if you look at this diagram right here, it asks us to use the data in order to calculate the average rate of appearance of B from 0 seconds to 20 seconds. So what I'm going to do is I'm going to look at the final concentration of B, which is, assuming this is in 1 liter, let's say it's 0.46 molar because it's 1 liter. So that's its final concentration, so 0.46 molar minus 0 molar. And then I'm going to divide that by the time, so 20 seconds minus 0 seconds. And what I get for my average rate is 2.3 times 10 to the negative second molar per second. So that's how you find average rate. Now, what exactly happens to the rate as the reaction proceeds? Well, as you can see from this graph, another way of measuring the rate of change is simply the slope. And so if you look at the very top of this graph, you have a very steep slope. And as the reaction proceeds, the slope decreases and decreases until it's pretty much going to just level off. So as the reaction proceeds, the rate decreases. And that's key to know. And that's because you have less of your reactant left over. Now, the second type of rate that we can measure is an instantaneous rate. Now, the instantaneous rate is the rate at a very particular instance. And so what we do is we're going to draw a dot. Let's look at the 600 second, which is the problem we're going to do. And to find the instantaneous rate of that, I need to find the slope at that point. And so I'm going to draw a line that is tangent to that point. That line is already drawn for you in black with the purple right triangle underneath it. And then we're going to find the slope of that. So to find the slope, remember, slope is simply rise over run. And so the rise is going to be the change in concentration, which is going to be 0.017 minus 0.042. And you're going to divide that by the change in x, which is 800 minus 400. Now notice that this problem is a little bit quirky as far as the negatives are concerned. I personally would have put 0.042 in front of 0.017 and had the instantaneous rate be negative because that slope itself is negative. But the reason why they did that is because they're asking for the rate of disappearance, which implies that you're going to have a negative slope. So they're saying the rate of disappearance is 6.3 times 10 to the negative fifth. While if you just asked for the rate, you would have said negative 6.3 times 10 to the negative fifth. So notice for instantaneous rate, what you're doing is you're calculating the slope at a very specific point by finding a line that's tangent, taking the difference between the two different concentrations, which is the rise, and dividing that by the change in time, and then that will be your instantaneous rate. So rather than taking an average, you're looking at a specific time, 600 seconds. So let's actually look at reaction rates and how we can use our stoichiometry in order to determine reaction rates. Well, in this reaction here, the rate of disappearance of A is going to be the negative 1 over A, the little a being its coefficient, times its rate, equals negative 1 over B times the rate of B, equals 1 over C times the rate of C, which equals 1 over D times the rate of D. So this is how we use stoichiometry in order to determine the rate. So let's look at an example. It says, what are the relationships between the rates? Well, I know that negative 1/2 of the rate of N2O5 is going to be equal to 1/4 of the rate of NO2, and that's going to be equal to simply the rate of O2, okay? Now, the reason, why exactly does this matter? Why do we care about this stoichiometric relationship for reaction rates? Well, if I know the rate of one of them, I can actually determine stoichiometrically the rate of another. So here it tells me that my rate of disappearance of N2O5 is 4.2 times 10 to the negative 7th. What is the rate of appearance? And so what I can do is multiply that 4.2 times 10 to the negative 7th by negative 1/2, and I'm going to set that equal to 1/4 times the rate of NO2. And then all I have to do is solve for the rate of NO2 by multiplying both sides by 4, and I get 8.4 times 10 to the negative 7th. Notice I made the 4.2 negative, and that's because it's the rate of disappearance, making sure that the rate of NO2's appearance is positive. So the rate of something disappearing is negative, the rate of something appearing is positive.